Okay, so now we're going to go through an example of converting a Epsilon-NFA to an NFA using the algorithm mentioned in the lecture slides. So the first thing that has to be done is you have to compute the epsilon closure of each state. And what's the epsilon closure of a state? It's basically the set of all states you can reach by reading only epsilon transitions. Note that the epsilon closure of a state always includes itself, because from any state I can read nothing and stay where I am. So for example, the epsilon closure of S0 for this particular epsilon NFA includes S0 because I could always remain where I am, or I could epsilon to S1, or I could epsilon to S1 and then epsilon to S2, so I can reach S2 from S0 by only reading epsilon transitions. We compute that for the rest of these states. So the epsilon closure for S1, well, if I'm in S1, I can either stay where I am, or I can go to S2. So S1, S2. For S2, there's no outbound transitions that read epsilons, so it only includes itself. For S3, I could epsilon to S4, so that includes S3, S4. And then for S4, it again only includes itself. So now we've computed the epsilon closure for every state. What we do is we copy the DFA, or copy the epsilon NFA, I should say, and then remove all the epsilon transitions, and then keep all the standard transitions. And then we're going to add transitions based on what the original machine does. So the first step in the algorithm is in the new NFA, a state is accepting if we can reach an accepting state by epsilon transitions from an accepting state in the original machine. So the only final state in the original machine was S4, but S3 can reach a final state via epsilon transitions, so that makes S3 also a final state. Obviously S4 can reach itself reading epsilon, so that means S4 is still a final state, and no other states are final, because from any other state I can't get to S4 just by reading epsilons. So my new machine, S3 and S4, will be final. And what's the second part of the algorithm said? So the second part says we add a transition from state S to state T reading an A in the new machine if there's a transition from some state in the epsilon closure of S reading A to the same state T. So for example, in the original machine, there's a transition from S1 reading an A to S3. S1 is in the epsilon closure of S0, so that means there's a corresponding transition from S0 reading an A to S3. So basically it means whatever transitions exist for S2, we add those to S0. Whatever transitions exist for S1, we add those to S0. Because each state is included in its own epsilon closure, all transitions from the original machine that aren't epsilon transitions are like automatically added in. That's why we copied the machine to begin with. Because S0 is in the epsilon closure of S0, all transitions that involve S0 in the original machine are duplicated in the new machine. So what transitions do we have? Let's see the epsilon closure of S0. I have to duplicate all the transitions from S2 outwards. S2 has an outbound transition with a C, so that means I add an outbound transition with a C for S0, and that's all the outbound transitions for S2. S1 has a single outbound transition with an A, and we've already added that to S0. So now we check the next states. For S1, we copy all transitions that S2 has. S2 has a C to S4, so we add a C to S4 from S1. S2 only has itself, so there's nothing to do there. S3 includes S4 in its epsilon closure. S4 reads a B, goes to S2, so S3 reading a B will also go to S2. S4 only includes itself, and so that appears to be all the transitions. Curiously, we have that state S1 in the new machine is actually unreachable. There's no inbound transitions to S1. And the reason is because in the original machine, there were no transitions you could take to get to S1 while consuming a character. So because the only thing we really care about is that if strings are accepted by the first machine, they remain accepted by the second machine, instead of reading an epsilon to S1 and then reading the A to go to S3, we've essentially bypassed that transition and added a transition that goes from S0 directly to S3, which is corresponding here in the new machine. And because from S3 I can read an epsilon and go to the final state, that means the string A must have been accepted in the original machine, because I can epsilon to S1, read the A, epsilon to S4. And in the new machine, that's reflected because we have a transition from S0 reading an A to S3, and S3 is a final state because you can epsilon from it to a final state in the original machine, that is by this transition here. So given an epsilon NFA, that's how you convert it to an NFA. This is sort of a very strange machine. I've sort of judiciously chosen it to demonstrate the algorithm rather than it being a machine you might practically come across.